So now that you know what a semaphore is, you know a bit about what Java Semaphores can do, their structure, their functionality, some of the methods. Let's talk about how we can use all this stuff in order to do various kinds of example apps. So one, of course, is to mediate access to a limited number of shared resources, which you should be familiar with now with our Palantir simulator app. And the other is to coordinate the order in which operations occur. And we'll talk about that in the context of our ping pong app. So let's first start by talking about how Java Semaphores can be used to mediate access to a limited number of resources. So the app that you're doing, the Palantir simulator, is used to show how Java Semaphores can be used to limit the number of Middle-earth beings, like our good friend the Hobbits, and Sauron, and so on, who can gaze at a Palantir concurrently. And I think, if I'm not mistaken, I managed to find all the various characters that gazed into Palantir from the Hobbit. From the Lord of the Rings. So we got Sauron, Saruman, I think it was Merry, or Pip, I can never remember which one it was, Boromir, and Aragorn. So those are the ones who end up gazing. And each of these things, of course, is implemented to run in a separate thread. The app, as you know if you've been running it, can be configured to have a certain number of Palantir, 2, 4, 6, 10, whatever. And that internally, of course, is implemented by a semaphore. In order for a being to gaze, like let's say we have 2 Palantir that are waiting. In order for someone like Saruman to gaze, they have to acquire the semaphore. And once they get it, then that will automatically and atomically decrement the permit count by 1, so then that being can go and gaze. And if another one goes ahead and grabs another Palantir and starts to gaze, count drops to 0, so nobody else can go at that point. And in fact, that's actually happens in the movie or in the book, if you know that. And the other threads here we're going to have to block while these guys are off gazing into the semaphore, or gazing into the Palantir. Obviously, real-world applications don't use Palantir very much, but it's a stand-in for a very common class of concurrent problems where you have a limited number of resources you want to dole out and share. So can anybody think of some examples from everyday computing life that might actually use something like this? What would be an example where you'd want to do that? Bruce? Right, so you might have a limited number of threads, which probably means a limited number of cores. Like let's say you have a 4-core machine and you want to do some image processing with it. But to keep the thing from being completely unresponsive while you're doing image processing, you might say, I'm only going to let 3 cores be in use at a time so that 1 core can be used for me to interact with, read email or surf the web or whatnot. So you could bound the number of processor cores you want to devote to something or other. So that would be one example. Another example might be some kind of a floating license server where you say, if you spend $10,000, you can get 5 concurrent floating licenses. So up to 5 people can be using this tool at one time. And if the 6th person comes along, they have to wait until someone else releases the permit. And actually, a lot of license servers work that way. So this is not at all an unrealistic use case. Whenever the permit's released back to the semaphore, another thread can acquire it and start to go. So we might have a case where Saruman releases it, and then Merry can go ahead and grab it. Actually, I think it was Pip. He was the fool of a toque. Pippin grabs it, and he can gaze. And this is an example of fully bracketed acquisition and release, right? So whoever owns it needs to be the one to give it back. If it didn't work that way, you'd have really bizarre use cases where someone was gazing and then someone else was like taking their Palantir and ripping it out from underneath them and giving it back to the pool, which would be kind of strange. Here's a sequence diagram that illustrates the interaction between the various parts of the program that's doing this stuff. So as you can see, we have the interface, the Palantir presenter UI part. We have all the beings that are out running as threads. We have Palantir. Excuse me, and let's say for sake of argument that we have 1, and then we have the Palantir manager, which is going to manage all these things. So we start out, the program starts, All the threads are kicked off, so they're now up and running. Each of the threads has their own stack, so they all run concurrently. They're all going to go ahead and call acquire on the Palantary manager. Let's say, for sake of argument, that we've got a count of 2 as the Palantary count. So in that case, 2 of them will acquire Palantary. 1 will block. Then the ones that acquire it are going to be able to gaze for some random amount of time between some predetermined max time or range. And then when they're done gazing, they go ahead and release. And in that case, another being will get a chance to acquire and gaze. So that's basically the flow of control of the program. And that's essentially how your assignment works. You might or might not see it quite that way, but that's if you were to sit down and draw out the visualization of the interactions between the different objects and the threads and so on. That's essentially what's going on under the hood. Okay. So let me show you a different use case where we're going to apply Java Semaphores to coordinate threads. So now we're going to coordinate the order in which threads are going to run. And this example is the ping pong app. And the way it works is we've got 2 threads, a ping thread and a pong thread. And if you run this app, it basically goes back and forth, pinging and ponging. So pong is black, ping is white. You ping and pong and ping and pong. So the screen will flash as it's pinging and ponging. And then it also is printing out which thread is doing what and which iteration we're on. So we ping and we pong, and it increments a count and so on. Think about it as it's the simple-minded version of the old video arcade game Pong, if you're familiar with that. I'm not sure why they didn't call it ping, but it's called Pong. So that's basically how it works. You can play around with the code. It's all written in Android, and it has actually a bunch of different synchronizers to coordinate the interactions between the threads. We're just going to focus on the semaphore one. Here's essentially what it looks like under the hood. We've got a master thread, which is the one that knows how to play ping pong, and we'll see what it does. We've got a pong thread and a ping thread, and then we have a ping semaphore and a pong semaphore. And we'll talk about how those things get initialized in a second. So when the program starts up, it creates 2 threads, ping and pong, and they're going to alternate back and forth, pinging and ponging, writing out to the display, and they do this using some cool Android stuff, which I won't talk about in detail now, but we might talk about this later if we have a chance to look more detailed at the code. When the threads start to run, then they have a common ping pong algorithm. They both run the same code using the so-called template method pattern. And the way that works is there's a piece of code called run or something like that, and it does the basic algorithm. And it delegates to acquire and release the appropriate semaphores, and it does that by having the subclass of these things know how to acquire and release the semaphores in the right order. So let's take a look at what that might be. So what's going to happen is we have the ping semaphore and the pong semaphore. Those are 2 semaphores that are created during startup. And the ping semaphore starts out with a count of 1. Keep in mind these are binary semaphores, or they're being treated as binary semaphores. They have 2 states, acquired or not acquired, where acquired is 1 and not acquired is 0. So if you create a semaphore with a count of 1, what that means is if anybody tries to acquire it, they'll always succeed because it starts out not acquired or unlocked. Conversely, the pong semaphore starts out with an initial count of 0 because that one's intended to be acquired or locked. So what's going to happen here is that the 2 threads will start up. They'll both go and try to acquire their respective semaphores. The ping thread will try to acquire the ping semaphore. The pong thread will try to acquire the pong semaphore. And of course, the ping semaphore will succeed because the count's 1, but the pong semaphore will not. So the pong semaphore will block. And here's what it looks like under the hood. Keep in mind that this example does not fully bracket access to the semaphores. So the one that acquires it is not the one that releases it. In fact, the whole way this works is if we end up with the whole reason the program works is because we have 2 semaphores and they take turns letting the other guy get a chance to run. So here's what happens. The ping thread starts up. Remember, the ping semaphore starts with a count of 1. It comes in here, and it doesn't matter whether the ping thread begins to run first or the pong thread begins to run first. Doesn't matter. Let's say, for sake of argument, the pong thread starts up first for whatever non-deterministic reason. And it goes and it tries to acquire the pong semaphore. Well, recall that the pong semaphore started out with a value of 0. So when you try to acquire it, it's going to block, right? Because its count is 0, and you can't make progress by trying to acquire a semaphore whose count is 0. So this, no matter where they start, this guy's going to block. In contrast, the ping thread will come along, and the ping semaphore has a count of 1. So it's going to acquire it, decrementing it by 1, so now it's atomically been decremented. And then it goes ahead and it prints out ping. And then what it does, notice what it does. This one is locked now, right? Ping is now locked. It will now release the pong semaphore. And it'll loop back around again and try to acquire the ping semaphore. Well, guess what? The ping semaphore has a count of 0 because we just locked it here. So it's going to block. So it's going to get one chance to write ping, and then it's going to have to wait. Meanwhile, after calling release on the pong semaphore, that increments the count by 1 of the pong semaphore. So this thread over here that was blocked in acquire, waiting for the count to be greater than 0, is now magically and atomically incremented to be 1, which means it can acquire it, which atomically decrements it by 1, so it's now locked. It turns around and writes pong, and then it turns around and it releases the ping semaphore, right? So it increments that by 1. That's now no longer 0, it's now 1. This thread can wake up and say, aha, now I can get access to this thing. So it will atomically decrement it, print ping. Meanwhile, this guy will have looped back around again, found his semaphore to be 0 because he had locked it here, and so on. So you can see that these just alternate going back and forth, pinging and ponging, and incrementing and decrementing each other's semaphores by the appropriate amount. Well, they typically decrement theirs, and then they increment the other one. And by doing that in a collaborative way, then they can coordinate the interactions in the program. Any questions about that? Common question people often ask when they want to get really clever is they say, can't we do this with just one semaphore? Why do we need 2? Can't we just have 1? And my response is always, try it and see. And it turns out you really cannot easily do it with one semaphore unless you build lots of other stuff into your program, and even then it's hard. But 2 semaphores makes it easy because you're just coordinating, letting each other go. And in a sense, it's kind of like the original reason why people built semaphores in the first place, which was to coordinate access to stuff, like a shared railroad track. Okay, so that's the interaction diagram. Here's what the code looks like. Each of the threads has a semaphore called mine and other, and they're just initialized in inverse ways. And so acquire will always try to acquire my semaphore, which blocks until the semaphore has a count greater than 0. And release always releases the other semaphore. And of course, when the 2 threads are created, mine and other are shifted. So they're different in each one. And once again, notice that this is not fully bracketed. So they take turns doing this stuff. The thread that acquires the resource is not the one to release it. Okay, and then the way this program works, just to kind of close the loop with our earlier discussions from a couple weeks ago, after all the stuff runs in the background, the main thread, the ping pong thread guy who's playing the game, will simply wait to join on the exit of both other threads. So the main thread doesn't exit until the other ones are done. And that turns out to be important because for various reasons, we don't want the program to continue to let people start the program to play again until the current round is finished. So now that we've talked about what a semaphore is, we talked about how Java semaphores work, we've seen a couple of examples of Java semaphores illustrating different features and use cases of using semaphores. The last part of this lesson talks about usage considerations. What are effective ways of using semaphores in practice? So semaphores are a lot more flexible than some of the simpler Java synchronizers, which we haven't talked about in any detail, but you probably have a vague awareness of some of them. So one is the synchronized statement, which is done by putting the synchronized keyword with a so-called intrinsic lock, or almost any object in Java can be used in this manner, but in this case, we have a method that's going to essentially do some stuff, and this region of code here is going to be synchronized. Likewise, there's this thing called the reentrant lock. We'll talk more about that later. That is also used in the same way. Semaphores are a lot more flexible. Why are they more flexible? One reason they're more flexible is you can atomically acquire and release multiple permits with a single operation. So just like you can beam down multiple members of the away team in one transporter beam exercise, so too can you acquire and release multiple permits with one operation. And I gave you some examples of where that might be useful, like buying the tickets from StubHub and so on, or buying the tickets from Ticketmaster. Likewise, unlike synchronizers, such as synchronized statements or reentrant locks, the acquire and release methods do not need to be fully bracketed. So that gives you some additional flexibility. That's good. When you use semaphores to coordinate access to a resource pool, such as our good friend the Palantiris, or the Palantiri, it does a very specific thing. It tracks the number of free resources. So it tells you how many there are that are available. However, the semaphore by itself, or a single semaphore by itself, does not track specifically which resources are free. It doesn't really know the resources it treats are just the count of the resources rather than the individual resources. And for that reason, you need something else in order to be able to figure out which resource someone can get access to. So thinking about your Palantiri simulator app, the Palantiri manager uses a semaphore to figure out how many available Palantiri there are, but to get a specific Palantiri, to get the next free Palantiri, something else has to be used. In your case, it's a hash map, right? So you have to do that. And in fact, it turns out that the semaphore isn't even protecting the hash map. The hash map needs to be protected from concurrent access. Why does it have to be protected from concurrent access? Because if the Palantiri count, the semaphore value, the permit count of the semaphore is, say, 5 or whatever, then if multiple threads come along, they'll all simultaneously, let's say 4 threads come along, or 5 threads, however many, as long as they're less than or equal to the count, all those things will be able to concurrently descend into the critical section. And if you don't protect the hash map or the list or whatever data structure you're using, then chaos and insanity will break out, and there'll be race conditions and other visibility problems accessing that data structure. So you're going to need to have other ways of not only selecting the appropriate resource, but selecting it in a thread-safe way. And that's, in your current assignment, assignment 1B, what you're doing with the spin lock. Later assignments, next assignment, you'll be using a reentrant lock and other stuff. So the point is that you can't just get by with a single semaphore alone. If you want to get access to the resources individually and then control access to them, requires even more stuff. It turns out that there's a number of traps and pitfalls to using semaphores. And this will end up being the case for almost all the lower level Java synchronizers, things like reentrant locks and stamp locks and so on. And these things can be tedious and error prone. Why is that? Well, let's take a look at an example. One common problem is to acquire a semaphore somewhere and then return or break out of the scope in which the semaphore was acquired without releasing it. Now, of course, if you don't need fully bracketing, this may not be a big deal because someone else may be responsible for releasing the semaphore. But in cases where you need fully bracketing, then if you bail out without releasing it, then it's been acquired. So that resource is lost. It's kind of like going back to the example from the beach volleyball tournament I was telling you about. If 2 teams go and play and then they forget to return the ball, then even though the court's not in use, nobody else can play on that court because the ball hasn't been returned. So a common way of avoiding this problem is to use this particular try finally idiom. And this is very widely used whenever you want to make sure you release a lock. And in your programming assignment, make sure that you do this properly. You want to make sure that you're releasing things like spin locks and other stuff within try finally blocks, because that way you can ensure that they always get released even if you bail out due to an exception or whatnot. Keep in mind your semaphore doesn't work quite that way because you have two methods. You have acquire Palantir and release Palantir. So you don't want to be releasing the Palantir in the acquire method, right? That would cause problems. But you will be acquiring and releasing the spin lock or whatever synchronizer we use later. And for that type of synchronization where it's fully bracketed, this is a nice way to do it. Sadly, or not sadly, depending on your point of view, Java does not have the concept of a destructor the way that C++ does. So there's no way of being able to bake in automatic release into the object itself. But the try finally model is the next best thing. And that's the idiom that you follow in Java to do all this stuff. Another thing you can do is hold a semaphore for a very long time without actually needing it. So you're not releasing it quickly enough, and therefore things will end up degrading. So here's an example where we acquire a semaphore, go into a loop that does something that doesn't require the semaphore, and then only after we get out of the loop do we go ahead and release the semaphore. Well, there's no reason to keep it locked this long, and locking it this long may end up degrading performance because there's other threads that are being kept at bay when they in fact should be in there doing something useful. So that's obviously a problem. Yet another problem is releasing the semaphore more times than needed. So here we're going to acquire the semaphore, do some stuff, and then through whatever mistake, we say release, release, release. Now all of a sudden the count's been kicked up quite positively, and other threads that come along may get access. We started out with a count of 1, now it's got a count of 3, and that's just bizarre, and that may damage other parts of your program, which really wanted to minimize the amount of concurrent access to some resource. And you've just made it larger. So that's obviously a problem. And those are all sort of typical things that go wrong when you program a semaphore. So you have to be careful how you use semaphores in practice. The typical way of doing this, by the way, is not to expose these low-level synchronizers directly to programmers, but instead to build facades or frameworks or classes that hide the implementation details of locking behind more abstract interfaces. And then it becomes an implementation detail how the actual synchronizer is used under the hood. And we'll talk about a couple of patterns later in the course, things like monitor object, things like active object, a couple other patterns, half sync, half async, and so on, that do exactly that. They shield the low-level details of synchronization from the upper-level parts of the program. So all you see as an application developer is just a method call on an object where there's no synchronization exposed, so there's nothing that can go wrong, at least not from an accidental point of view. And therefore, you push that stuff to be an implementation detail.